In the last lecture, we considered the comparison test, and we saw the difficulty associated to that, namely that we had to establish an inequality, and that's not always trivial. Luckily for us, there is a simpler test known as the limit comparison test. Which goes as such. Consider, let AN and BN be series of positive terms. So you are adding terms that are bigger than or equal to 0. And suppose further that the limit as n goes to infinity of one divided by another exists and is L. If L is between 0 and infinity, then both series converge, or both series diverge. In other words, both series behave in the same way. Let's prove this. Well, I'll give you a flavor of the proof. I won't prove it in complete detail. But look back at your limit. If the limit exists and is L, what does that mean? That means that for large N, AN over BN is very close to L. Or, if you prefer, AN kind of looks like L times Bn. So you see you have this relationship between A and B. The A's and the B's kind of behave in the same way. And that's what the conclusion is saying. Both series will converge or both series will diverge. This series is pretty much L times this one. So they behave in the same way. Let's consider a few examples. In fact, let's reconsider the examples we were looking at in the comparison test. Remember, in the comparison test, you had to come up with some sort of inequality. Our first example, I believe, was 1 over n squared plus 3n plus 2, where we showed that this term was less than or equal to 1 over n squared. In the limit comparison test, we don't need to do that. Here, if we just look at the denominator, the dominating term is n squared. So we're going to do a limit comparison with the series 1 over n squared. And what do we know about this series? We know that this is a convergent P series, where in this case P is equal to 2, which is bigger than 1. So we're starting out with a convergent P series. Let us apply the limit comparison test, which tells us to take one of these divided by the other. Or, if you flip, this is n squared over n squared plus 3n plus 2. You can do as n goes to infinity, this has the form infinity over infinity. So you have options. You can do L'Hopital's rule, or you can factor out an n squared from the bottom. Let's do that. This is 1 plus 3 over n plus 2 over n squared. The n squares cancel out nicely. As n goes to infinity, 3 over n goes to 0, 2 over n squared goes to 0, leaving you with a limit of exactly 1. 1 is between 0 and infinity. So both series converge or both series diverge by the limit comparison test. But you started out with a convergent series. So this series converges by the comparison test, by the limit comparison. We had also looked at the series (1 over n minus 1). Again, we showed that this was bigger than 1 over n. It was relatively easy to do that. But if we apply the limit comparison test, we don't even need to worry about which one is bigger, which one is smaller. Here, the dominant term in the denominator is n, right? This minus 1 here is negligible. We're going to do a limit comparison with the series 1 over n. What do you know about this series? You know it's a divergent P series. Where P is 1, which is less than or equal to 1. If we do the limit comparison, it's going to be the limit of one term divided by the other. It doesn't matter which one. Makes no difference. Let's mix it up. This one divided by that one. Or, if you prefer, n minus 1 over n, which is 1 minus 1 over n. Or you can do a L'Hopital's rule, or you can factor out an n from the numerator. Bunch of options. And that limit is easily seen to be not 0, but 1. Once again, 1 is between 0 and infinity. Right? In the limit comparison test, you have an issue if you have a limit of 0 or infinity. You want to stay away from those. What does that mean? If you get a limit of 0 or infinity, it usually means you did not choose the right series to compare it to. You either chose it too large or too small, depending on which one you put on top, which one you put on the bottom. This limit is between 0 and infinity, right? You have a finite limit which is bigger than 0 and less than infinity, so both converge or both diverge. In other words, both series behave in the same way, but you started out with a divergent series. So this series diverges by the limit comparison test. Let's look at the third example we had done, where both of these were easy enough to treat using comparison test or limit comparison test. But here, in the comparison test, the inequality was tricky to come up with. It wasn't obvious. You'll see, though, that in the limit comparison test, there's almost nothing to do. The dominant term in the denominator is n cubed. This minus 1 here is negligible for large values of n. So we're going to do a limit comparison with the series 1 over n cubed. So 1 divided by the other. Again, it doesn't matter which one is on top, which one is on the bottom. You are dividing by a fraction. We're going to multiply by the reciprocal. This is n cubed over n cubed minus 1. Let's factor out, well, let's do a L'Hopital's rule, just for fun. We already did a factoring out business. If we, right, I mean, this has the form infinity over infinity. We can apply L'Hopital's rule. Derivative of the top, derivative of the bottom. And now it's clear that this limit is 1. Once again, 1 is between 0 and infinity. So both series converge or both diverge. We started out with a convergent p-series, where p is equal to 3, which is bigger than 1. This series converges, so this series converges by the limit comparison test. In the next video, we'll do some exercises from the book using both comparison and limit comparison tests.